Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Rhonda Franklin, Professor of Electrical and Computer Engineering at the University of Minnesota. Rhonda, thank you so much for joining us today. To get us started, can you tell us a little bit about yourself and how you got involved in engineering and nanotechnology?
Sure. So I was raised in Houston, Texas, and I loved math and science as a kid. And so I was always fascinated with how things work and why, and just very curious naturally. But I love math because it was a form of a symbolic language to me. And it was very similar to English and grammar. So I thought it was kind of cool. I actually ended up getting in engineering because I had math and science teachers who really, really were very supportive of me in school. And they made suggestions. And one of the suggestions was to go to an engineering camp that was at the University of Houston. So I went to this camp, and that was my first exposure to what is engineering. And a really, really nice professor, his name is Dr. Pascas. And he organized that program. It's called MESET at the time. And it was there that they had professors to come and expose us to what is engineering. So I learned what is engineering. I used process of elimination to take away the things that I didn't think were going to work for me for various reasons, and ended up selecting electrical engineering as the direction of choice. And so I went back to high school and said, I think I'd like to be an engineer. My teachers helped me prepare for that. And then I applied and went to Texas A&M for undergrad.
So your current research is electrical engineering. It's work toward communication systems. Can you talk a little bit about your research and how it involves nanotechnology?
So the interesting thing about the work that I do is we are interested in waves. And you can think of waves as being water waves. If you threw a pebble in the water in a pond, you'd see a wave move. But another way to think about a wave is to visualize the letter S and to rotate it 90 degrees so that it's sideways. And that's like one wave. And what we do is if you chain them together, that would make a lot of waves. And we study how those waves move through things. It either moves through a structure, which is guided, or it moves through air, which is wireless. And so I was fascinated with electromagnetics as an undergrad, because it was the closest connection between math and electronics. So when I realized that you could use math to describe how signals look and move, that was just really intriguing to me. And over time, I learned that electromagnetics was the basic principles that help people develop communication systems. Now, it's funny that you'd ask me about nanotechnology, because when I was an undergrad, I didn't understand anything about the difference between engineering and a technology. Like, what does that really mean? And it turns out that when I was an undergrad, we had microelectronics technology, and now we have nanotechnology. And so for my purposes, nanotechnology is a way for me to make circuits that function in a communication capacity. And because I was working in my training as a microwave engineer, microwave engineers are mostly responsible for developing a lot of the foundational work for communication systems. And I work in an area or an aspect of microwave engineering that has to do with chips and integrated circuit chips for communications. And then that was originally done with microtechnology, which basically means that the designs are around the feature size of micrometers. Now, the common person actually knows what the communication system looks like, at least parts of it, because when you look at the top of a building, you see antennas. Now, you don't see the rest, but you see the antenna. So most communications are all of those big physical hardware systems, except they're made in a really, really small form on a chip. And in microwave engineering, we learn how to take big structures and make them small geometric shapes to make a chip to perform the same function of sending a signal from point A to point B, the way that the base stations, which is what's at the top of most of the buildings, the same way that they do their job. And the fundamental difference is that they use a lot of power. And if you do it in a chip, we call that low power. So back to nanotechnology, As you go up in frequency, the physical dimensions in a chip form of an electronic circuit get smaller. That's a natural thing. But as I get smaller, microelectronics technology fails me. It has physical features that are undesirable and cause me to lose a lot of energy when signals run through them. So much so that if I get to a certain frequency and I use those same methods, I would lose most of my energy just pushing it through the signal. And so whatever I put in, I might not get anything out because it's all consumed in the electronics. So I became fascinated with nanotechnology for two reasons. And it was about 2 decades ago, before it was ready for prime time. Number one, I thought, if we could do this, we could get rid of a big issue that causes circuits to be lossy, and that's surface roughness. So if things are really small, I need a way to make them so that the roughness associated with it is really small relative to the whole size. So at microns, when I'm using microelectronics technology, what's great about it is the surface roughness, right? That would be equivalent to, like, if you think about concrete is made of sand. But the surface roughness in concrete is very small, right, compared to, say, bricks. So we want the same kind of smoothness when we look at the way signals move through our physical structures. So microelectronics was great when we were doing micrometer size designs because surface roughness is really small, like maybe 1% or less. But if I make things really, really small, like on the order of 1 micron, now that's not acceptable. So I need to go to another method. I need another technology that allows me to make something much smaller and maintain this same level of smoothness in the surface roughness because my signals can go through that without noticing that the roughness is present. So that was my first reason for thinking, that would be great. But the other thing that is really, really fascinating about nanotechnology and the role it plays in where communication systems are going in terms of higher frequencies and the like is that letter S that I told you about. If you visualize the letter S, again, sideways, so it's tilted on its side, if I put one dot, if I just kind of put a dot along each edge, that dot would represent a very small fraction of that whole letter S. When physical components are really small, like smaller than a dot, they behave really differently than if the physical component is the same size as the whole letter S. So what we like is when they act like a dot, they follow really simple design rules. When they act like an S, they require more complicated design rules. So as I go up in frequency, my S gets smaller, which means the dot I need is smaller, which means that microns become too big because now I'm taking up like 3 dots instead of 1 dot. And therefore, if I can use nanotechnology, I can now use simplistic circuit design rules because my physical structure can be much smaller. So there are 2 main reasons that inspired me to say, I really would like to figure out how can we integrate nanotechnology into the way we make circuits. And so I guess if I were to recap, I would say, one is that the way you make it has much lower surface roughness, which means my circuits and my signals will love it because they'll flow through there without noticing it. And the second one is that the physical size associated with nanostructures means that I can use much simpler circuit design rules to get the same functions that I would at lower frequencies where the features are much larger.
I really like the way you described that, and I think I'll come back to that in a moment. But I want to just hit on a couple of concepts that we often hear when we talk about research at the nanoscale. And one of those things is interdisciplinarity in collaborations. And in your work, can you describe the types of expertise that you bring together and the collaborators that you share your work with?
So that's another thing that's been really fantastic for me is 20 years ago when I was interested in the concept of nanotechnology, it quickly occurred to me that I don't have the skill set to do nanotechnology. So I did dabble in it once with a student and we made some progress, but it became quickly clear to me that I cannot get another PhD in material science because I would never get to work and I would be able to pay for it anyway. So what I did is I was waiting. I have a colleague in my department, Professor Stadler, who is an amazing material scientist. And she works on magnetic materials. And she and I had been trying to find a way to work together for almost a decade. And eventually what happened is my work was progressing the way that it does in terms of learning how to, really expand my toolkit for circuits, for communication applications and measurement methods. And she was expanding her toolkit and coming up with these really clever ways to make nanostructures. She makes nanowires, and she makes them with all different types of materials because that's her expertise. And one day we bumped into each other in the hall and decided, hey, I had this idea and I wanted to share it with her. And over a cup of coffee, we etched out a concept, wrote up a proposal, it got funded, and we had our first project together, which is how we started doing nanowires. And my group started doing characterization of those wires. A few years later, I had a chance to work with another colleague because remember I told you that the nanostructures are more suitable for really high frequencies. 20 years ago, when you talked about terahertz technologies, that was more philosophical. I mean, people were doing it, but it was more philosophical. And whenever I would bring this idea, people would say, so what can you do with that? And I was like, well, you can imagine. And of course, that was not very interesting to a lot of people. But 20 years later, what you could imagine was now becoming more interesting and more feasible, because our communication systems are starting to approach that realm, because we need that spectrum space to do a lot of things that we're trying to do. So I was visiting a colleague and working with her on a project. And I said, I really want to do this project on interconnects. I'd like to be able to show that we can come up with really low loss interconnects for terahertz applications, and that would allow us to interface with nanotransistors, which right now they have to use microscale connections to do. And it works, but there's some issues there. But I don't have a way to make the measurements. Well, she has a way to make those measurements. And I know that those measurements are challenging because I make measurements, and my measurements are pretty high, but not that high. So she was interested, and I pitched an idea with her and brought my nanowire colleague on board. My colleague that I'm doing with the high frequency with is Professor Henderson at UT Dallas, and Professor Stadler is at University of Minnesota. So we pitched an idea, sent it in as a proposal, and it got selected. And what's really cool about this project is the first project was selected by the National Science Foundation. And that was great with the nanowire characterization, because that allows you to really do more discovery. We're trying to understand, and we're trying to ask questions about what we're doing, how we're doing. And because Professor Stadler and I had worked well together on that, we learned how to work that, those two pieces together. And then when I got an opportunity to get the second project funded, this is actually funded with a different kind of organization. It's the Semiconductor Research Corporation. Well, that corporation, the projects are only selected if industry's interested. And I've been wanting and trying to work with them for years, but I just didn't have all of the pieces together. And so when they showed interest in that abstract, which then led to a proposal that got funded, it allows the three of us today that what we're working on now, which is nanowire-based interconnects for terahertz applications. So those three pieces had to come together in order for us to do the project we're doing now. And that work is going really, really well right now. So I'm so excited. We got our first paper accepted for it. And the students, there are 3 students working on it. They're all learning from each other. They're presenting to industry. It's a really wonderful opportunity for everyone involved.
Well, it sounds like a great opportunity. And I think when students can learn from each other from different disciplines, like you mentioned earlier in your career, and then also to understand kind of the constraints from industry and what their needs and their timelines are, that's a great lesson for students. The way that you've described your work today makes it clear to me that you understand the importance of science communication, and that you make an effort to consider how to explain really complex concepts in a way that are understandable. I just wanted to ask you to share some experiences you have working with students and what advice you give them if they want to go into nanotechnology, and how you inspire them.
The biggest thing to me is allow yourself to be curious, because being curious requires you to become comfortable with not knowing the answer. And that's really scary for this generation of students, because they are so much more prepared than any generation I've seen in terms of their background knowledge. But for me, I think when I'm looking at students, I'm number one looking to see what are they interested in? Have they allowed themselves to think deeply about what they want to do? Asking themselves, what am I interested in doing? Am I willing to ask questions? Am I willing to experience failure? Because to do good research, you have to be willing to fail to find the right answer. And the other thing I think is also really important is being willing to work in spaces that are less familiar so you can learn from people who really know more about what you're trying to do than not. I think when I look at this particular project that I'm thinking about, the one I just described, even in my own group, my students have always done design, fab, and test. And when they come into the lab, I always ask them, okay, I have these three things. What do you prefer? What do you like? What would you do and you would lose track of time over? So I always know if I take a student in, which one of these three that they have a propensity to. I've always tried to design the specific project around their strength, but then allow them to interact with another student who has a strength in an area that is not so strong, where they're not as confident. And it's hard, right? Pushing yourself to go do something that's not comfortable is not easy. But the most amazing thing is when they do finally get there and do it, they are so excited because it's a huge accomplishment because it was difficult. But the other thing is that it's like an immediate feedback loop that I don't have to tell them things that they figure out because they're involved with this try process, right? That all of a sudden, if I have to make it, I realize that what I'm modeling doesn't factor in what's really going to happen in the testing because I made this thing and what I just made is not what I'm modeling. When you farm these things out to other people, it's too easy to blame the other person for why it's not working, when actually it may have nothing to do with the people. It may just be that there's poor communication around what you're actually doing. And so this is what I've always done with my group when we were doing our work. With the multidisciplinary work, what's been interesting to me is, everybody's quite proud of what they do, but eventually you start to see them see that, oh, I didn't think about that. And all of a sudden, they start bouncing off of each other and saying, well, I could do this and I can do that. And you see this, I guess, like a Venn diagram. You see that the overlap domain starts to grow and they start to really find a play space that they can engage in. And I think that's just really exciting that, the kind of problems we're trying to solve require complex solutions. Complex solutions require multidisciplinary teams, interdisciplinary teams, and transdisciplinary teams. And I'll explain what I mean by that in a second. So because of that, that's not part of our training. Our training is to create a person who's disciplinary and to be good at be general as an undergrad, specialized as a master's, expert as a PhD. That's the way it works. But the kind of problems that we need people to solve require them to be comfortable with the idea of working with other people who are of like ilk in their own domain. But who owns that training process? So research projects are the space where that can tend to occur. Senior design projects might be a space in undergrad where that can occur. But it's not a space that exists, but it's also not a space where any of us are experts at teaching anyway. Like, how do you get a degree in how to teach interdisciplinary research, right? That's not a degree for anybody. I'm working on some centers right now that are transdisciplinary in nature. And that is not trivial, because it's one thing to have techie people talking to each other who are in different disciplines. What do you do when techie people are now talking to people in social science and people in liberal arts and people in medicine who in their own right are experts? And how do we find a common play space for that? And I'm very grateful because the project that I worked on with Professor Stadler, the first one, we were using the skills we developed for communications to model and characterize her materials. But the application was actually for nanomedicine, which meant it brought a it brought a medicine person in, it brought a vet in. And I literally spent a year feeling pretty dumb because they were using words I had never heard. But the interesting thing is, if you allow yourself to be vulnerable enough to feel dumb and ask a question, all of a sudden it challenges them to find a simple way to explain it because they know you don't have any of the background to understand it at the level that they're communicating. And then when they explain it where you get it, You ask other questions of things they've never thought of, because what I know as an expert is sometimes you're blinded by your expertise, right? And so collectively, that project produced many, many interesting outcomes because these four people have very different backgrounds, me, an electrical engineer, Professor Stadler, material scientist, a veterinary person who studies cancer, and another guy who studies a specific aspect of cancer. We were all kind of talking together, and over the course of 2 years, we could coherently talk about that particular problem. Nothing else now, but that really narrow problem. And it really excited me because I want to prepare my students to be able to do that. And so I learned, and then I come back, and it made me change how I do some things with my students, just because I know they need the practice time to kind of get used to this idea. But I've gotten notes back from a few students, just through LinkedIn or whatever, and, saying, hey, I wanted to thank you because, I had an advantage over my peers. You encouraged me to ask questions, and it was okay that I didn't know the answer, and we figured out how to figure it out. And that makes me feel good because, on the educator side, it's a lot like parenting. So a bit of a thankless job. You don't really know if it's appreciated until later when they benefit from it. And so I'm sort of at that point in my career where people can come back and they're moving up and succeeding in their own way. And they're thinking, they're a little bit more reflective. And it's nice to hear that back because I don't know. I'm like, was that a good experiment or a disaster? I hope it was good, but I don't know because it's, I live in a feedbackless loop when I'm dealing with students a lot of times.
No, I can completely relate with that. And I just want to thank you so much for that story. I think looking at the interdisciplinarity and the experiences that you shared are just a great reflection of what we hear about the NNI and how important this interdisciplinarity is. So thank you so much.